Everybody.
It's a pleasure.
Thank you.
It's a pleasure to introduce the second speaker of the morning, Nicos Georgiou from the University of Sussex. And he will talk about time-fractional G, G1 queues and applications to the double auction model.
Thank you very much. Thank you for the invitation. It's nice to be at the real conference after 2 years and a month. And I will be talking about this time-fractional queuing systems. I'm a bit obsessed with technology. Is everybody able to hear me online? Any reactions? Okay, I see chat, so maybe yes. I hope it doesn't say we cannot hear you, right? Yeah, okay, great. Great. So I will be talking about these time-fractional queuing systems. I will talk about several of them because there are many ways to do them into time-fractional queuing systems. And I want to start with a quick layout. My ground state is always discrete stuff, and I will start with discrete Markov chains, and those are great because, for example, you can do simulations and you can do statistics. You can find Kolmogorov equations. You can do birth and death processes, which are super applicable. In particular, you can go to Ehrenfest-Earn, which is super well studied. There is the MM1Q or MMKQ or whatever versions of Markovian queues you like, queues in tandem. This can lead to the double auction model, which I will talk about later. Hopefully, I will have time. And from the point of view of discrete Markov chains, usually you care about the mixing times, convergence to equilibrium, and then you want to know limit theorems and equilibria of all these processes. So when I want to do a time-fractional chain or semi-Markov chains, still several of these things remain. Like you can define time-fractional birth and death processes or fractional Kolmogorov equations where there is the Caputo derivative there. But now one starts wondering if all the other things are okay. Like, is the mixing time now well defined? What does it mean to converge to equilibrium, especially if you have a finite chain? Can we have limit theorems to equilibria, but there is something different there just because you don't have moments. In this case, the inter-event times are Mittag-Leffler. The Q now becomes, instead of MM1, it's a GG1Q. And again, the limit theorems and equilibria depend how you change time and what interpretation of the original Q you have. And the double auction model, again, it depends how you change time. And in itself is quite a very complicated model. So what I'm going to try and do is sort of mention some stuff about all this orange that you see here. So I will talk about a Mittag-Leffler Q, and there are many ways to define it. So I will start from the discrete MM1. There you see some particles already. And I want to build from that several versions of this Q. So the discrete version says that with some probability beta, I stay as I am. No particles come in, no particles go away. With some probability 1 minus beta alpha over A plus B, a particle comes in. And with whatever probability you need to make it 1, a particle leaves from the Q. And what you see here is that the Q length is, for example, 4. And in applications, this is one question that you are interested. How big is the Q length? Will it hit 0? Is the chain ergodic? Will it hit 0 infinitely often? So my servers can take a rest and so on. So there are two different ways that I want to sort of make this this Q. This is what I call the singly fractional Q. Essentially, there is one big background counting process, and then every time an event happens in that counting process, I will flip a coin to decide what the Q does. So let me just set up some notation. I call R1 and R2 these quantities. Lambda would have been the rate of the Poisson process if I wanted Markovian. But now I want the inter-event times to change, and I want these Mittag-Leffler times. So what you see there is just the CDF of the Mittag-Leffler distribution. And for a Q like this, you actually get this type of Kolmogorov equations where the derivative there is the Caputo derivative. And this particular Q is actually well studied. You can find Q length, you can find the distribution, you can find moments. LA there will be the Q length, alpha will be the index of the Mittag-Leffler, and we have an expectation for the Q length. I would be the initial Q length here, and the J you see over there would be the Riemann-Liouville fractional integral. And then you can also compute the variances. The moment you start you want to compute all the moments, these equations become more and more hairy. But indeed, you can have several nice equations that describe everything you want. Now, all of this can be found in a paper by Ashone, Leonenko, and Pirozzi, and they have expressions for the PGF of this type of Q. Actually, there they have more general Qs. They have the Erlang Q, which is like a Q, but there is like K phases of the serving. And then with Enrico and Jacob, who is our joint PhD students, we sort of found the moment generating function and expression for all the moments in some sort of recursive way. But this is a nice Q, and this is one way that you can take the actual discrete MM1Q and fractionalize. I want to talk about a different way, but before I do, let me talk about limit theorems in this particular Q. Well, the expression I have there, nu n would be the counting process. That's how many events you have up to time t. Qij will be the discrete kernel, the n-step transition for the discrete chain, and f bar will be the cumulative, the complementary cumulative distribution function for the Mittag-Leffler. And this is one way that you can write down the expressions for the jump probabilities in this singly fractional Q. And there is an ergodic regime for that, for the discrete chain, meaning that you will hit zero infinitely often, which is a good thing, if the probability of removing customers is higher than the probability of putting customers in, which is reasonable. And it's an irreducible aperiodic chain, and as such, the discrete transitions converge to equilibrium. And just because of the equation that I have there for the continuous time version and the fact that the QIs themselves converge to the PJ, then the limit of the PIJs is still the same invariant distribution for this Q, which in fact is geometric. And you can sort of say, okay, even if I fractionalize time this way, my Q will eventually converge to its invariant distribution. And the question is how? So if I have this type of fractional Q with Kolmogorov equations, where like I showed before, indeed the limit is the geometric distribution, and we can go just a step more, and we can do something about mixing times, and we can find the finite T epsilon such that the total variation distance between the transition probabilities and the invariant measure is less than epsilon. And now the question is, what can we say about this T epsilon? Can we quantify it well? Do we know when this convergence will happen? The answer is yes. But I will only show you the result if the Q has a capacity, just to make it a finite chain, because it's a bit easier. Just to remind everyone, the total variation distance between two measures is just the supremum over all events of their difference. And it's a number between 0 and 1. For countable spaces, this becomes really cute. It's just 1/2 times the sum over all changes. And the mixing time for discrete Markov chains is the smallest possible n, such that that distance over all states is actually less than epsilon. And it's very convenient, since I'm doing the continuous Q, to sort of alter this definition a bit, because the thing, I mean, I don't have discrete steps anymore. I have this counting process. So I would like to take the expected value of this total variation distance and make that less than epsilon. So there is this continuous mixing time for the discrete chains. So what we have is, it's actually quite nice, because we are borrowing from the theory for discrete Markov chains, where the embedded mixing time is known and well calculated for several chains, has something to do with the spectral gap. All of this can be found. And what we are doing is that we are bounding this t tilde up and down, essentially with the embedded time to the power 1/β. Beta will be the index, the power index of the Mittag-Leffler. And then we want to know how this epsilon comes into place. And for the upper bound, we have the 1/β, but unfortunately, the lower bound falls a bit short. And this is true for all alpha in 0, 1, but unfortunately not 0. Otherwise, it would have been a really sharp inequality there. And this gives you, for example, if you are doing simulations, it sort of tells you that after that time, you are actually at equilibrium, so you don't need to simulate any longer, which is one thing if you care about computational complexity of such things. So here's one simulation that we did on the RFS chain. This is just after the lower bound. Actually, maybe we cheated a bit and we made alpha like 0.01 or something like that. And you see that, and the red is actually the equilibrium. So you see how close they are over there. And this is just before that lower bound over there. And here already you see that you are not at equilibrium, right? There is some distance. So this is what we have for finite chains, including Qs with capacity. And to push this on the infinite space, it's actually a bit more delicate, because you need to worry at what point at the tails of your equilibrium measure. But in this case, it's going to be the geometric, and the tails are exponential, and everything is nice. So now I want to change how I am I'm fractionalizing time. In the discrete setting, what I'm describing here is equivalent. In the case that I will do a fractional change, it's not equivalent at all. So I want one Mittag-Leffler counting process, fractional Poisson process, pushing particles out from the Q. And I want another one pushing particles in, completely independent from the other one. Discrete and even Poisson MM1s, they don't care about what I just did. The distribution is the same. Here, there is a difference, and we still want to understand the Q length. So here you have, I want two different fractional Poisson processes, one for arrivals, one for departure. The arrivals is the blue, and there is the new lambda counting process. And the departures is the red, and there is the new mu counting process. And I want to join these two so I can understand the Q length. So I will let it run. You will see the particles coming and going according to what the green is doing. And what essentially I'm showing you here is precisely the equation that I have in the box that tells you that in order to find the Q length at any given time, you need to subtract the two processes, but then you also need to subtract the infimum of their differences up to time 0. So here, I'm subtracting the red from the blue. In this case here, you want to have a departure before an arrival, so nothing happens, right? The Q length cannot go less than 0. And here, finally, you have your first arrival, so that's why you go up. Now the red tells you you need to go down because you're losing a customer. And then the blue tells you, okay, another customer comes in. And this is how the whole process evolves. And I have that wonderful expression about the queue length that can be used to find scaling limits, for example. Usually I would have given you like a second to sort of convince yourselves that my formula is true, but I don't think I have time. So let me show you some simulations of this particular queue. What you see here is that the power index of the Mittag-Lefflers is the same, is 0.7, but I am using the time scale to sort of see the behavior of the queue. So here, the lambda would be the scale of arrivals, and mu would be the scale of departures, while the power is the same. And here, I'm sure you can convince yourself that this looks like a transient queue length, transient queue. Here you see when they are flipped, and again, this looks like a very ergodic kind of queue. And here I even have the scales the same. So same power, same scales, just independent entries and removals. And again, you see that it should be somehow ergodic, but you have longer periods with high queues. And here it's what happens if I have different betas. And this is even more transient than you expect. And here is what you see if you have different betas, but in favor of removing customers, you just have these bursts of excitement. And all of these actually we can quantify, which is nice. I just want to talk about the limit theorem. I'm sure everybody in this audience knows, but let me just refresh just in case. So here we have what we call the alpha stable subordinator. It's a Levy process with that Laplace transform. And then we can take the inverse alpha stable subordinator, which is essentially the level sets. And then we change time of the Poisson process using that inverse alpha stable subordinator. And that's how we get the fractional Poisson process. And we have the following theorem. If I take the queue length, I have two independent fractional Poisson processes with powers alpha 1 and alpha 2. I want to know what is the maximum of those. And I have two different scales, lambda 1 and lambda 2, one for arrivals, one for departures. And I divide by t to the maximum of those power indices. So there are three different cases. If arrivals win, that's when alpha 1 is larger. Then the weak limit in the J1 topology, and as t grows, will be essentially the inverse stable subordinator. If alpha 2 wins, with the scaling, the limit is actually 0. And if they are the same, then my Q expression actually converges to what you expect it would converge weakly into this expression between the two different independent subordinators. So y tilde there would be an independent version of y. And here are some simulations that this is without the scaling, but they demonstrate the point. So the scaling here, I think in all of these, the larger beta is 0.99. So more or less the scaling is around the time index, which is like 1,000. If you divide that, you have a non-decreasing process, a transient Q. That's the first case. Here, if you divide by about 1,000, it will completely collapse to 0 because the highest Q we ever had up to that point is 5. And here you will have the most interesting thing, which is this third branch, because this will not be completely 0. The two independent subordinators would sort of flip with each other. Okay, so these are the results for the Q. And now I want to use this to build the double auction model, or to sort of discuss the double auction model. But again, I will try and transform it starting from a discrete Markov chain first. Hopefully, I'm a bit conscious of time, but we'll see. Great. So here's the double auction model in some generality. This is used a lot in finance. Sometimes you will find this as the limit order book. And it has what we call limit orders. So you can buy, and an order drops at some bid value, indicating willingness to buy a given asset at that particular price. If nobody's taking your offer, this stack up, right? So you can have something like this. You can also sell if you have the asset and you choose a price that you want to sell the asset. And again, if nobody's picking it up, you can also stack up on this side of the value. And this will never mix, right? There is no chance that somebody wants to sell somewhere where people are asking, because they want to sort of push them towards profit. Now, this can happen interchangeably, and prices come up and asset values either in bids or asks are dropping down. And sometime you will have the most forward asking price and the most backward selling price. And those are what we call the best bid and the best ask. And now, after all of this thing is happening, we have market orders where they start eliminating this. Essentially, there somebody was willing to buy at the best bid, or you can sell, and somebody there was willing to buy the best ask. And this again move interchangeably, as also orders are coming down, and there is essentially 4 possible, if you want to see it as a Markovian thing, there is 4 possible Poisson queues here, or 1 or 2, depending how you wish to generalize. So it could be that all of these are happening with one background counting process. It could be that these happen completely independently with 4 different counting processes. And if it is Markovian, it doesn't matter which thing I choose. But if it's not, it does. So I would like to make a simplification where I don't have anything asking, all the asking things that are coming actually buy, and I want to study this only with people that are willing to sell. They are willing to sell on these prices, so many of them at so many price, at that particular price. And then whenever an ask comes, the front one completely disappears. So you can do a birth and death projection here. Essentially, if you have a background Poisson process with rates adding up to 1, let's say, you can have that prices drop down independently at rate Qi at position I, and then you have a removal rate, which is P, and you want to know how many of these you can clear, essentially. And this is half ergodic, half transient system, meaning that if you are removing orders fast, you can remove the front lines if P is relatively large, and otherwise the rest will just stack up. So I'm really, really conscious of time. So we can see this actually as a birth and death process in the first M coordinates. This is the discrete version, this is the continuous version, and this is what we want to fractionalize somehow. And we can interpret this as a birth and death or an MM1Q, and all the things we have for the GG1Q or the MM1 fractional Q work. Or you can do it like this, and you can do the whole vector together, and this becomes like a random walk. And again, there is a different way to fractionalize this by putting independent fractional Poisson processes on every side. And you want to study the joint, how many orders you have in each coordinate. This is just 2 because I cannot draw 3D. So I will I will stop. This is just to tell you that we can compute stuff at equilibrium. We can also compute convergence to this equilibrium because again, everything is nice, but the equilibrium is only in the first m positions of this model, right? It doesn't happen in the transient bit because you cannot remove all the orders in principle. Okay, so let me quickly mention this next step. First of all, we would like to study the full version, not the simplified version. However, there are ways to sort of reconcile the two, and Enrico and collaborators have worked on the Markovian version of this. This is open. We are trying to sort it out. What happens if I put independent fractional Poisson processes everywhere? Hydrodynamic limits can be obtained. This is for a non-Markovian, but still you have moments in your inter-event times. There are SPD models. There are state-dependent price dynamics. There are diffusion approximations. And then we also want to study what happens to the process of the best bids and the best asks. And all these papers are all quite recent. In fact, the model is quite old. It has been studied easily since 1981, at least that's how far back I went. But all these exciting things are happening now. So I will stop here, and thank you very much for the attention.
Okay, let's thank the speaker. And are there any questions here?
So, Nicos, what you said about this limit for your Q? So you said that it's possible to write the limiting equation. So it will be the limiting fractional equation for your Q.
No, we didn't check the fractional equation. No, we can only study these weak limits of the.
So you do not have this.
Yeah. No, it's actually quite challenging to see what's happening.
It's an interesting question.
Yeah.
Okay.
Any more questions here? Are there questions online? No, we don't.
I do not see any raised hands over the Zoom. However, you may unmute yourself and ask a question if you may have.
Okay, if there are no more questions, then let's thank the speaker again.
Thank you.
And we are right on time for the tea break, and then I'll see you all back in half an hour.